Type a query into Google. Get 10 blue links in 100 milliseconds out of a corpus of 100 billion pages. That is not a miracle. It's an algorithm. And it hasn't fundamentally changed since 2009. BM25. Term frequency, inverse document frequency, length normalization. That's it. And it still beats a lot of what came after, until it doesn't. And then you need something new. Welcome to video 3 of lecture 9. Information retrieval. The field that Google was built on, and the piece of the stack that quietly powers every LLM chatbot when it needs to actually cite something. Because retrieval is what makes RAG work, and RAG is why LLMs finally stopped hallucinating quite so much. Video 2 showed us translators using cat tools with translation memory. What is a translation memory? It's a specialized search engine. Every source segment is a query. The engine returns the closest matches. That is information retrieval. Same math as web search, just applied to a smaller, curated corpus. This lecture keeps finding the same tricks in every application. Today's puzzle. When you ask a modern chatbot a factual question and it gives you a citation, a real one, not a hallucinated one, where did that citation come from? The model didn't just know, it searched. The search happened over a database of documents using techniques the IR community has been sharpening for 50 years. And that search is what separates confidently wrong from actually helpful. Today's 3 beats. First, BM25, the keyword-based retrieval scoring function that ate the world. Robertson and Zaragoza 2009, 3 terms. TF, IDF, length normalization, still the default in Elasticsearch and Lucene. Second, dense retrieval. Embed the query. Embed every document. Nearest neighbor in vector space. Karpukhin's DPR paper 2020 handles semantic matches. BM25 misses. Third, retrieval-augmented generation. RAG. Lewis 2020. Retrieve documents, feed them to an LLM as context, generate the answer. The core pattern behind every citable chatbot answer. Beat 1. BM25. The idea is deceptively simple. For each document, count how often the query terms appear. That's term frequency, TF. Then discount the terms that appear in almost every document, the, and, of, using inverse document frequency, IDF. Rare terms are more informative. Finally, normalize for document length so that a 100-word snippet doesn't automatically beat a 10,000-word essay. The magic. This scoring function isn't learned. There are 2 constants, K and B, that you tune by hand or with cross-validation. Set once, forget forever. No neural network, no training data, no GPUs. And on standard IR benchmarks, BM25 is still competitive with fancy neural retrievers for a huge range of queries, especially queries where the user typed the exact keyword they wanted matched. Where BM25 breaks, when the user's query and the document use different words for the same idea. Query car repair. Document uses auto maintenance. BM25 gives 0 credit, no shared tokens, same meaning. This is the vocabulary-mismatch problem, the reason we spent lecture 5 building word embeddings. And it's the wedge that let dense retrieval into production. Beat 2. Dense retrieval. The idea. Take a transformer encoder like BERT, feed it the query, get out a single vector, 768 dimensions. Do the same for every document in the corpus ahead of time. Store all those document vectors in an index. At query time, encode the query, find the k nearest document vectors in cosine similarity, return them. That's it. 2 engineering catches. 1. Training. You need query document pairs that are relevant and hard negatives that aren't. Getting good hard negatives is the whole game. 2. Inference. Nearest neighbor over 10 million vectors is slow, so the field spent a decade on approximate nearest neighbor libraries. FAISS from Meta, ScaNN from Google, HNSW graphs. These libraries are why dense retrieval is a real product and not a lab demo. In practice, nobody ships pure BM25 anymore. Nobody ships pure dense either. Everyone runs a hybrid. BM25 catches exact keyword matches, model numbers, error codes, quoted phrases, dense retrieval catches semantic paraphrases. You combine the two ranked lists with a re-ranker on top, often a cross-encoder that scores every candidate directly. That's the actual production stack. BERT-3, RAG, Retrieval-Augmented Generation, Lewis et al. 2020. The recipe: take a user's question, retrieve the top few most relevant passages, concatenate them into the LLM's context window. Ask the LLM to answer using only that retrieved context. The model gets fresh information it wasn't trained on, and it can cite the passages it used. Hallucination drops. Trust goes up. Why RAG matters so much for products. LLMs are frozen. A model trained in early 2024 doesn't know what happened this month. RAG lets you plug in a live corpus, your company's internal docs, yesterday's news, a legal database. The model doesn't have to be retrained, just the retrieval index, which is why every enterprise LLM product on the market is a RAG system with a chat wrapper on top. Where RAG breaks: chunking. You have to split long documents into passages before indexing them, and the wrong split destroys context. Retrieval failures. If the retriever doesn't find the right passage, the LLM confidently makes something up. And context stuffing. Even with a 1,000,000 token window, dumping 50 passages in front of the model degrades attention. RAG is not a solved system. It's a wet cement engineering problem that every AI startup is currently pouring. 3 takeaways before the quiz. 1. BM25 is a hand-tuned scoring function, TF, IDF, length normalization, and after 50 years it's still competitive. Robertson and Zaragoza 2009, runs on a CPU, no training data required. 2. Dense retrieval encodes queries and documents as vectors and finds nearest neighbors. Karpukhin's DPR 2020 handles semantic matches, BM25 misses. In production, it's always hybrid, BM25 plus dense plus a re-ranker. 3. RAG, retrieve, then generate. Lewis 2020. The pattern behind every citable chatbot. It's how LLMs know about anything that happened after their training cutoff. And it's still wet cement. Quiz 1. Which 3 quantities does BM25 combine to score a document against a query? A query embedding, document embedding, and cosine similarity. B term frequency TF, inverse document frequency IDF, and document length normalization. C page rank, TF, and cosine similarity. Or D softmax score, attention weight, and cross entropy. B. TF, IDF, and length normalization. The scoring function has 2 constants K and B that get tuned once and stay set. No training data, no GPU, runs in milliseconds. Robertson and Zaragoza 2009 is the canonical reference. Quiz 2. What does dense retrieval fix that BM25 struggles with? A speed. BM25 is too slow for web-scale search. B. Vocabulary-mismatch. When the query and the relevant document use different words for the same concept, BM25 gives no credit, but a dense encoder gives a similar vector. C. Ranking of exact keyword matches. Or D. Storage requirements. Dense vectors are much smaller than an inverted index. B. Vocabulary-mismatch. Query car repair won't match document auto maintenance under BM25 because they share no tokens. A dense encoder sees them as close in vector space. This is exactly why word embeddings from Lecture 5 matter. For Retrieval 2. Quiz 3. In a RAG, retrieval-augmented generation, system, what is the LLM's job at query time? A. Retrieve the top passages from the vector index. B. Train a new embedding model on the corpus. C. Read the retrieved passages inside its context window and generate an answer grounded in them, usually with citations. Or D. Compute the BM25 scores for every candidate document. C. The retriever finds the passages, the LLM reads them, and generates the answer. Because the answer is grounded in retrieved text, it can cite. That's how modern chatbots know about events after their training cutoff. The freshness lives in the index, not the model. Back to the puzzle. Where did the citation come from? From a retriever, BM25, or dense or hybrid, running over a corpus your LLM never trained on. Retrieval is the piece that makes LLMs finally citable. 3 applications down, 7 to go. Next up, pulling structured facts out of unstructured text. Information extraction. Next time, pulling facts from text. Information extraction. Relations, events, and Ezione's OpenIE dream. How Google Knowledge Graph got built. Hit subscribe.